Here's an interesting fluid mechanics problem which you can actually find in the Pathfinder Physics for Olympiad book. And it's not only aimed for students who are about to take their Physics Olympiad, but it's also for students who are about to take the JEE main or advanced exams. But it's also aimed for students, for engineering students in their first year, as long as they're doing some form of fluid mechanics. So let's try to read the question and let's see what it wants from us. Now, if you'd like to see anything similar to this on the channel, please let me know in the comments. If you have any suggestions for any specific problems you'd like to see, then that's good as well. So we're dealing with a water tank, and in the water tank on or along the bottom right edge, there's a slit which extends into the screen, and we've got a wedge into that slit. And then we start pouring water. And the question is, how much water or to what height can we pour the water so that the wedge doesn't leave that slit? Okay, and we're given a couple of things here. So we're given that the mass of the wedge is m, and then we also know the angle theta. We're also given the coefficient of static friction between the wedge and the right wall, and we also know the width of the tank, so this is how much the tank extends into the screen, and we also know the water density rho. Okay, now why would the wedge pop out from that slit? That's the first thing we have to consider. So what's happening here is that the more water we put in the tank, the more displaced volume we've got. Okay, so if we have this much water, then essentially this is the amount of displaced volume. If we have this much water, then the displaced volume is going to be higher, basically. And the displaced volume is proportional to the buoyant force, to the upthrust, right? Like this. So this buoyant force, this vertical component of the pressure force, is proportional to the volume of the displaced fluid. And obviously, the more liquid we put in, the more displacement we get. And the bigger the force, the more likely we are to push the wedge out of the slit. And we want to find what is that limiting height at which the wedge is still in the slit. Okay, and the way I would suggest to do this is by first of all drawing a free body diagram. So this is what we have. I'm going to draw all the forces that are acting on this wedge. So first of all, we have the weight. Okay, so this wedge has a certain mass, so it's got a weight which is pulling downwards. Then we have a normal force, which is perpendicular to the wedge as well as to the wall, to the right-handed wall. And what actually keeps the wedge from moving besides the weight is the friction. Okay, so the friction is actually acting downwards, and the friction as well as the weight, those are the two forces keeping the wedge from moving. And the force that is actually trying to push the wedge out is due to this pressure that's acting. So let me call this Fp from sort of like the pressure for the force due to the pressure sort of. And the first thing I would try to do here is find what this force is. Okay, and we know a couple of things, so we can actually find it quite easily. So let's look at what's happening along this surface of the wedge. Okay, so let's say that we've got the water level until here, and we've got the water level at a height h or depth h, and I'm going to measure my y-coordinate downwards from the free surface of the water. Okay, and then the other thing we know is this angle here is theta, right? Which means that this angle here is also theta. So what I'll do is I will consider what happens at a certain depth y. Okay, so I'm gonna go down at an arbitrary depth like this. Okay, and at this depth I'm going to try and find what is the infinitesimal force at that location due to the pressure. Okay, so in other words, I'm gonna find this df. So this df is rho g, and then this is multiplied by y, right? So this is the hydrostatic pressure so far, and then we multiply this by the area, okay? And the area is given by the length of that infinitesimal element, which I'm going to call dl, okay? And I'm going to come back to that in a second. And then we multiply that by b. Okay, b is the distance, is the width of the water tank into the screen. Okay, so that's it. Now the problem is that we have two variables here. We have y and then we have l. Okay, so let's try to combine them, or not combine them, but let's try to only use one, either y or l. And the way in which I'm going to do this is as follows. So this distance here is my y, and this distance here is my l. Okay, so we can change the variable by doing a bit of trigonometry. So we can say that cosine of theta, I'm talking about this angle here at the top, and I'm looking at this triangle here, is equal to y over l, which means that l is y divided by cosine of theta. So now I'm going to take this and I'm going to put it in here, but before that I will have to obtain the differential dl, which is dy over cosine theta. Okay, and now we can actually get an expression for the force, so that's rho gy, and then I'm going to put the b here as well, and then instead of dl I have dy over cosine theta. Okay, so we know what is the infinitesimal force at a certain depth y. So what we can do now is we can find what is the total force due to the entire water depth h. Okay, and to do that we're going to integrate. So we have that the force is integral of df, and that is going to be equal to, so I'm just going to copy what df is. So rho gy b, and then dy over cos theta. And we know what the limits of integration are as well. So y starts from 0, which is at the very top, and it goes all the way down to h. So this should be from 0 to h. And I'm going to take out all the constants to make things a bit easier. So this is rho g b over cos theta, integral from 0 to h of y dy. Okay, so this is rho gb over cos theta. This is a very easy integral, right? It's just y squared over 2 from 0 to h, which gives us, finally, that, let's use blue to be consistent with the free body diagram. So this is rho gb over cosine theta multiplied by h squared over 2. Okay, so this is not FP, this is, I call it FP, like the force due to the water pressure, the hydrostatic pressure. And that's it. So this force is acting perpendicular to the surface. Okay, so we found what this force is. So what I would then do is I would split this force into its horizontal and vertical components. So there's a component like this, which I'm going to call fx, and there's another component like this, which I'm going to call fy, and then we have to figure out where the angle theta goes, and angle theta should go here, okay, because this is perpendicular to this and this is perpendicular to this, so the angle between fx and fp is the same as the angle theta. So here's what we have that fx, that's the horizontal component of this force, is equal to fp multiplied by cos theta, which is rho gb over cos theta multiplied by h squared over 2 cos theta. Right, the cosines cancel out, which gives us that fx equals 1 over 2 rho gbh squared. Okay, and then we can do the same thing with fy. So fy is actually equal to fp sine theta, and in the same way, you can figure out that this is 1 half rho GB and then h squared, and then you have sine over cosine, which is tangent of theta, and that's it. So this is Fy. So now we're going to use those to write down an equilibrium of forces, okay? And this is what we have. So if we look at all the forces acting in a horizontal direction, we only have two, right? We have Fx and we have the normal force N. So we've got Fx minus N equals 0. There's no acceleration, nothing is moving. So N is equal to Fx, which is equal to 1 half rho GBH squared. Okay, now we only found what this force is in terms of other variables that we sort of know, but what we actually have to find is the depth h, okay? And to be able to do that, we have to look at the vertical equilibrium as well. Okay, so in the vertical direction, this is what we have. We've got one force acting upwards, that's Fy, and we have two forces acting downwards. So we've got Fy minus mg, and then minus the friction, Ff, is equal to 0. Now, this equation, as well as this equation, as long as the wedge is stationary, those two equations are true. Now, what the question is asking us to find is what's the depth or what's the height h at which the wedge just pops out of the hole of the slit. And at that particular moment, something interesting happens, namely friction, right? So this friction here becomes maximum, okay? And when friction becomes maximum, that is just before things start moving, just before the wedge starts moving upwards, we have that Ff max becomes equal to mu static times n, okay? So this is the friction that we're interested in. So essentially we have to take this and put it in this equation. So, and we kind of know what that is because friction is mu times n, but n is this. Okay, that's what we found from the horizontal equilibrium. So that's 1 half rho g b h squared. Okay, so that's friction, and now we're gonna put everything together and finally find what h is. So let's look at Fy, right? So Fy we calculated previously, so that is 1 half rho g, and I think it's bh squared tan. So bh squared tan theta. Okay, so this, remember, this is Fy, okay, and then minus mg, so I'm just writing the term, I'm writing the same equation basically. Minus mg minus, and instead of friction, I'm going to write mu times m. That's what the maximum friction is. So I'll start with 1 half again, and then I'll put the mu, and then I have rho, and then I have GBH squared. So GB and H squared, and the whole thing is equal to 0. So this is one equation with one unknown. The only thing we don't know here is H, so all we have to do is just rearrange this to find what H should be. So I'm going to factorize H squared, and what I'll get is the following. Actually, I think I can factorize a bit more than h squared. I can factorize 1 half rho gb as well as h squared, and this is going to give me tan theta. And then from here, what I'm going to be left with is just mu. Okay, and this is going to be equal to mg if we put minus mg to the other side. And therefore, h squared will be 2mg divided by rho gb times tan theta minus mu, and of course we can just square root this to get h by itself. And that's what we get, right? So 2mg over rho gb tan theta minus mu. Let's see which one satisfies this. Of course, another thing that we can do is just simplify the g's, right? And we're going to end up with 2m over rho times b, and then we have tan theta minus mu. And the one that looks like is the correct answer is actually A, right? So A is exactly what we got, and A is the correct answer to this question. And that's it.